propagation. Here is one of the key references used to develop this class. There is nothing more important in the education of geophysicists than developing their understanding and intuition about how seismic waves propagate in the ground. Suppose that you are in a dark room in the library, surrounded by a multitude of books. You are looking for a particular book. You will need a flashlight to guide you to the specific row and column where you can locate this desired book. The problem with oil and gas exploration is quite similar. We are trying to see through a dark and compact Earth, and seismic waves are just one of the flashlights which help us to see beneath the Earth's surface. We will try to help you develop this intuition and a good understanding of seismic wave propagation. We will use this understanding to describe various types of seismic surveys in future lectures. Wave propagation is a topic of broad appeal in sciences, with broad applications including classical mechanics, aerodynamics, meteorology, earthquake seismology, medical imaging, defense, and more. Our objective here is to familiarize you with the phenomena of wave propagation and with the physical laws which govern seismic wave propagation, namely the elastic wave theory. We will introduce physical quantities which enter into this theory, namely seismic sources, internal forces, displacement and strain, and the physical properties of rock formations. We do not have access to snapshots of wave propagation in the Earth. We are limited to data from sensors on or just below the surface of the Earth, or in boreholes. So we have to make sure that sensors effectively measure the desired physical quantities, and that they are adequately distributed. Another objective of future lectures are to describe the current and emerging distributions of source and receivers, that is, seismic acquisition geometries in seismic experiments. Here are some of the learning objectives of the lectures on wave propagation and acquisition. The concepts of P waves and S waves. The difference between generating waves in a fluid and in a solid. The difference between recording waves in a homogeneous fluid and in a solid. The difference between anisotropic and isotropic media. The difference between anisotropy and heterogeneity. Here is the plan we will follow for the first lecture of wave propagation. Let's start by looking at wave propagation. We consider a medium of piecewise continuous regions separated by interfaces, where the medium parameters, or medium physical properties, are discontinuous. When we make an explosion, a disturbance of a very short duration occurs at the point of impact. While the deformed area returns to its initial equilibrium, the disturbance gradually expands away from the point of impact. Let's watch. As illustrated here, the disturbance varies with time and position in space. The speed at which the wave moves from one point to another depends on the physical properties of the medium. This property, and others that we will introduce later, allow us to use wave propagation to probe media, even those as complex as the subsurface. Here is another example, a homogeneous media. Again, when we make an explosion, a disturbance of a very short duration occurs at the point of impact. While the deformed area returns to its initial equilibrium, the disturbance gradually expands away from the point of impact. Let's watch. As illustrated here, the disturbance varies with time and position in space. The speed at which the wave moves from one point is now constant. So far, we have assumed that media or rock formations at equilibrium state are made of piecewise continuous regions, separated by interfaces, where the medium parameters, that is, physical properties of the medium, are discontinuous, and the deformation and vibrations associated with wave propagation as continuous phenomena. This picture of wave propagation includes implicit assumptions that we need to clarify. Here is a better illustration of wave propagation. In practice, we divide the medium into grids that we call particles. Let's repeat this. In practice, we divide the medium into grids that we call particles. During the wave propagation, the particles are displaced and even deformed. Yet, after some time, the particles return to their resting state. Our goal here is to describe with some specificities the concepts behind the wave propagation. Here are some questions that we will address. How do we describe forces which cause wave propagation in the first place? How do we describe the particle displacement and deformation associated with wave propagation? How are particle displacement and deformation related to the medium properties? How do we describe the forces which restore the particle to resting state? What is the actual definition of a particle, and what are the assumptions behind the notion of particle? Let's now talk about the continuous medium assumption, which is the key assumption of seismology. A material is considered continuous if it completely fills the space it occupies, leaving no pores or empty spaces, and if its properties can be described by continuous functions. Like all substances, rock formations are made of atoms. They contain gaps or empty spaces. This feature is especially true for sedimentary rocks, which comprise most petroleum reservoirs. This picture shows a photomicrograph of a sandstone showing very fine laminations of dark brown humic, organic matter. The irregularly shaped blue spaces among grains are pores. here come the continuous medium assumptions. We will disregard the atom scale, that is, the microscopic scale, of rock formations and envision them without gaps or empty spaces. Furthermore, we will assume that mathematical functions, forces, stress, displacement, and strain, for example, which enter into wave propagation theory, are continuous, as well as the derivatives of these functions if they enter. Let's repeat this. Now we're talking about the continuous medium assumptions. We will disregard the atom scale, that is, the microscopic scale of rock formations, and envision them without gaps or empty spaces. Furthermore, we will assume that mathematical functions such as forces, stress, displacement, and strain, which enter into wave propagation theory, are continuous, as well as the derivatives of these functions if they enter. There is one exception to the continuous medium assumption: the physical properties of rock formations. These properties can contain a finite number of surfaces separating regions of continuity. Rock formations can consist of piecewise continuous regions, separated by interfaces, where the medium parameters are discontinuous. So the assumption of a continuous medium permits us to define stress, displacement, and strain at the particle scale, that is, the macroscopic scale, instead of at the microscopic scale or atomic scale. It permits us to use the laws of continuous mechanics to study seismic wave propagation and seismic data. In other words, seismology is based on laws of continuous mechanics. Seismology does not use laws of quantum mechanics. Again, seismology is the study of time-varying deformations of rocks contained in the subsurface. Although rocks are composed of atoms, we are concerned only with rock particles, which are small but yet contain many atoms. So the notion of particle is central to seismology, because modern seismology are only working at the particle scale. Within each particle, we assume that the atoms move in unison. The particle is often described as a very small cube, which is represented on macroscopic scale by point. Typically in petroleum seismology, the particle size is about 4 meters on each side. In earthquake seismology, the particle size is in the order of kilometers. The history of a given piecewise continuous elastic medium will be described by the position of each of its particles as a function of time. We will label the particles by the positions they occupy in space at the time t equals 0. The particle is specified by the coordinates with respect to a fixed orthonormal Cartesian reference frame with the origin and 3 mutually perpendicular base vectors, in which each vector has unit length. A particle is described as a point in the Cartesian coordinate system and is specified by the following. Let's make the following final remark about the continuous medium assumption. More and more, we have to work with measurements at a scale much smaller than the seismic scale. Therefore, a significant aspect of the microscopic scale has to be taken into account in macro models while maintaining the use of laws of continuum mechanics. For this reason, we will consider anisotropic and even anelastic models of the subsurface that we will discuss later. Now we are in the position to explicitly define the notions of homogeneous and heterogeneous medium. Under the continuous medium assumption, a rock can be characterized as either homogeneous or heterogeneous. A rock is homogeneous if its physical properties are invariant with space and time. Otherwise, it is heterogeneous. Four particular cases of heterogeneous media are commonly cited in petroleum seismology studies. The 1D or one-dimensional case, in which the physical properties are invariant along the x and y axis and with time. That is, the physical properties vary along only the z-axis. The 2D or two-dimensional case, in which the physical properties are invariant along the y-axis and with time. That is, the physical properties vary along the x and z-axis. The 3D or three-dimensional case, in which the physical properties are invariant only with time. That is, the physical properties vary along the x, y, and z-axis. The 4D or four-dimensional case, in which the physical properties vary with time as well as with position. Here is an illustration of a 4D model describing the Gulfax oil field. This model varies in space as well as in time, with time being the fourth dimension. In this figure, the time variable takes only two values, 1985 and 1999. The 1999 survey, shown at the bottom, clearly shows the effect of production when compared with the baseline survey of 1985, which is shown at the top. The change in the seismic reflection strength of the top of the reservoir is related not only to the saturation change, but also to the original oil column height. When water replaces oil, the acoustic impedance in the reservoir increases, causing a dimming effect on what used to be a strong response from the top of the reservoir. The strong seismic response from the oil-water contact in 1985 has also been dimmed due to production. Red and yellow colors represent a decrease in acoustic impedance, while blue colors represent an increase in acoustic impedance. Structure and fluid content are shown in the cross-sectional models on the right. Interpretation shows that the smaller oil accumulation, which is to the left of the fault, has been drained by 1999, while much oil is still to be recovered from the main accumulation, which is to the right of the fault. Let's now introduce the notion of stress tensor. Here is the question we are addressing here. How do we describe the forces which restore the particle to resting state? The displacement of each particle imparts on its adjacent particles by pulling and pushing. The stresses responsible for the pulling and pushing are related to a point, that is, particle. Elastic waves are associated with the local motions of the particles of a solid medium. Particles are displaced, then restored to their initial positions after time. The forces responsible for restoring a particle to its initial unstressed position of equilibrium are internal to the medium. We will call them internal forces or stresses. As we pointed out earlier, the displacement of each particle imparts on its adjacent particles by pulling and pushing, just like surface forces act on the boundaries of a medium. However, unlike surface forces, the stresses responsible for the pulling and pushing are related to a point, that is, to a particle, x, rather than a surface. Hence, if we describe particles as volume elements, the stress at a point can be described as a set of surface forces acting on the faces of a volume element at time, also known as t. These forces are not necessarily perpendicular to the faces of the volume element. Their orientation is arbitrary. Furthermore, these forces are generally different in both direction and magnitude for each face, because a given particle does not act on its adjacent particles the same way. To specify these stresses, a three-component surface force, that is, traction, is required for each face of the volume element. The traction forces, or force per unit area, acting on the area element facings, are as follows. Consider the traction force, shown in yellow, acting on the area element facing the positive x direction. The second subscript, x, in these components indicates that the surface is perpendicular to the x-axis. Notice that the traction, Tx, depends on the particle position and the time. Here is a good way to remember the description of stresses. The stress acting on a plane is a vector quantity. The diagonal elements are called normal stresses. Those are shown in yellow. The other elements, that is, non-diagonal elements, are referred to as shear stresses. Let's repeat that. Here again is shown a good way to remember the description of stresses. The stress acting on a plane is a vector quantity. The diagonal elements are called normal stresses. They're shown in yellow. The other elements, that is, non-diagonal elements, are referred to as shear stresses. Stresses at a point, here represented by an elementary volume or particle, are represented by a stress tensor. That is, a matrix whose columns contain vectors that transform like a second-rank tensor. This figure illustrates traction forces, which are parallel to the outward pointing normal vector for faces. If the area of each plane is A, the stress tensor is as follows. The forces produce non-zero shear stresses. Notice that forces will tend to rotate the volume rather than compress or extend it. However, for this volume to be motionless, F1 must be equal to F3. These results can be generalized to other shear stresses. In the previous example, we saw that the following conditions on components of the stress tensor must be satisfied for any medium in equilibrium. Thus, there are 6 independent stress components instead of 9. The stress can therefore be written as a 6-component vector. Let's repeat this. In the previous example, we saw that the following conditions on components of the stress tensor must be satisfied for any medium in equilibrium. Thus, there are 6 independent stress components instead of 9. The stress can therefore be written as a 6-component vector. Here is the convention for writing the stresses as a 6-component vector. The first column represents the subscripts of the 6-component vector. The second and third columns describe the subscripts of stress tensors. Please note that you will refer to this table many times in your studies and even in your professional life. Then we have the following abbreviated notation of stress tensor. Normal stresses are first and shear stresses are second. Here is the stress tensor of a solid. Here is the stress tensor of a non-viscous fluid. For non-viscous fluids like water, traction forces are always oriented along the normal to the surface on which the surface forces act. Hence, the stress tensor for non-viscous fluids is as follows, where P is a scalar known as pressure. The minus sign introduced in this definition is purely a matter of convention. Now it's time for a quiz. Write this tensor in abbreviated notation. Let's now turn to particle displacement and strain tensor. Here is our next question. How do we describe the particle displacement and deformation associated with the wave propagation? Notice how particles are displaced and even deformed. They compress, expand, and even angularly distort. 2 basic notions, particle displacement and deformation, that is, strain. For a given particle located at x in equilibrium, that is, t equals 0, its displacement at t is a vector. To measure the particle displacement, a sensor must be coupled to the particle so that it can capture particle motion with time. Let's repeat this. For a given particle located at x in equilibrium, that is, t equals 0, its displacement at t is a vector. To measure the particle displacement, a sensor must be coupled to the particle so that it can capture particle motion with time. Making sure that the sensors are well coupled to particles is a very important technological challenge that petroleum seismologists are still wrestling with. Particle displacement is a continuous function with time. We sometimes take advantage of this fact by working with particle velocity or particle acceleration. instead of particle displacement. We avoid the definition of t equals 0. The deformability of materials is an important characteristic of wave propagation because the particle displacement is not a sufficient measurement of deformation. The classic example used to illustrate this point is a stone being kicked around. The stone will rotate and move, hence the displacement. And yet there is no deformation because all particles of the stone have maintained their relative positions. Strains are a set of relative displacements. They are a means of describing deformability, that is, change of shape. Strain is a tensor, the spatial derivatives of the components of the displacement field. Except in the immediate vicinity of the shot point, the shape changes of rock formations are generally very small, about 0.001% of length changes, and about 0.01 radian rotation. Hence, we limit ourselves to small strain. Let's repeat this due to its importance. Except in the immediate vicinity of the shot point, the shape changes of rock formations are generally very small, at about 0.001% of length changes and about 0.01 radian rotation. Hence, we limit ourselves to small strain. The three basic measurements of strain are length change, or longitudinal strain, volume change, or volumetric strain, and angular change, or shear strain. These are illustrated below. Longitudinal strain is a change in length per unit length. In the x direction, it is defined as follows. We basically subtract the length of the particle in the x direction before and after deformation and divide the result by the length before deformation. Here are all three components of longitudinal strain.
Volumetric strain, or dilatation, is a change in volume per unit volume. That is the volume of the particle after deformation minus the volume of the particle before the deformation over the volume of the particle before deformation. Because we are dealing here with small deformations, by neglecting the second-order terms, we can verify that the volumetric strain is well approximated by the divergence of the particle displacement.
Shear strain is a shear displacement per unit length. From this diagram, here are the definitions of tangent of alpha 1 and alpha 2. For a sufficiently small deformation, tangent alpha is well approximated by alpha itself. Therefore, the shear strain in the xz plane is defined by this formula. So here are the three components of shear strain. Here is the strain tensor. Notice that the strain tensor is symmetric. In non-viscous fluids like water, only changes in volume are possible. Therefore, the shear strains are 0 for non-viscous fluid. Let's now talk about rotation tensor. Because we are essentially concerned with small deformations in seismology, the ways in which the particle displacement can vary in the vicinity of some test, point x0, can be described by using a Taylor series expansion in the particle displacement about the point x0. Here is the series. The spatial gradients of the displacement constitute a two-rank tensor that is called the deformation tensor. This tensor can be split into symmetric and antisymmetric parts as follows. And Eij is the strain tensor that we have just introduced. Var epsilon is called the rotation tensor. To understand the origin of the name of var epsilon, let's introduce the following vector, which contains the three independent, non-zero components of var epsilon. If we assume that Eij equals 0, then the deformation is reduced to a rotation tensor. In the general case, the rotation tensor represents the rotational part of the local deformation, while the strain tensor represents that part of the deformation which changes the volume and shape of the particle. Note that P and S waves can be obtained from the divergence in curl of particle displacement, or particle velocity, as follows. Let's illustrate these results. Here are snapshots of the particle velocity containing P and S waves. Again, the fast waves are P wave. Let's now look at the curl and divergence of particle velocity. We can see that the curl only captures S wave and divergence only captures P waves. Remember that only volumetric deformation is possible in non-viscous fluids. Therefore, all non-diagonal are 0, and all the diagonal strains are the same. Here is Voigt notation of this strain tensor. It allows us to represent the symmetric strain tensor by reducing its order. Basically, the 3x3 matrix, or the second rank tensor, is reduced to a 6-component vector. Here's an example of simple shear. This is an example of non-static strains. Here is the particle displacement shown in this expression. Now it's time for a quiz. Write the following strain tensor in an abbreviated notation and define the unit of these strains. We have now concluded our discussion of the continuous medium theory, the description of stress tensor, particle displacement, and strain tensor. When we return, we will describe elastic stiffness tensor and wave equations. Thank you.